excitement. Really, the real excitement started with ChatGPT that was adopted by Microsoft. But Google is definitely in the business. Meta is in the business. AWS is also in the business with a lot of models and platforms, very different business models. So you don't hear so much about it. But there's also problems. And you've all heard about some of these problems. ChatGPT invented the sexual harassment against law professors. And these are all hallucinations. But some of them actually are becoming very real, right? So Air Canada just a few weeks ago paid money because of hallucination, a model they were using made. And just this is very recent, I think a week or 10 days ago, New York City actually put a chatbot, an OpenAI chatbot to help people deal with regulations, rules, other things about the city. And it turns out that the model isn't doing exactly what it's supposed to do. So these hallucinations are really important for us to understand, because it's not merely that the model is reading wrong information somewhere. Most of these are actually a reflection of the model making wrong decisions. And there are many, many other examples of model making wrong decisions that we just haven't heard about yet. But still, so it's important for us to think about where are we in this. And we are all excited. We are excited from Sebastian's presentation just earlier, and there are good reasons to be excited because these models are doing something good, something that was much harder to do before. And I think that if we know how to use these models, if we push them in the right direction, we will be able to use this to develop, the way I think about it, as assistive technologies. But at the same time, it's very important for us, especially in academic environment, but perhaps even more so in industry, to think about, are we misinterpreting the technologies? Because this is really important. If we do misinterpret, or a good interpretation or correct interpretation of where we are is going to help us to actually put the emphasis on the right things, and understanding how we can actually use these technologies, what are the limitations of technologies, what are the benefits, what are the risks that this technology has. And I'm going to try to provide, in the first half of the talk at least, a perspective. It's going to be a little bit different than the perspective that Sebastian gave earlier, on where we are and where we should go. And I'm going to start with a couple of disclaimers. So first of all, I'm going to give examples for multiple models. My intention is not to criticize any of the models or the companies. It's really part of the discussion. My goal is to just shed some light on the state of the technology. And also, I'm going to give examples that were collected over the last few months. Some of the examples where models do not work today, they work on these examples, and vice versa, because this is not completely linear. So let me start with one viewpoint that I have. I mean, I think that there is a big gap between what models can do and where the solutions that we need are. And I'm going to give this kind of scheme here, and the details here do not matter. I mean, there's a lot of data sets here, and many of us don't like these data sets anyhow. But the bottom line here is that on the right side, I put mostly data sets that focus on memorization. On the left side, these are more data sets that focus more on decision-making or reasoning. And what you can see here is that if you look on the left side, I mean, average performance of models is in the 50s. But these are decision-making tasks. We want them to be somewhere around 100%. And this is where the research should go. And the job of all of you, me, my students, is really to fill this gap between where models are out of the box and where we need them to be in order to actually use them productively, consistently, and reliably. So let me start the talk by going back 55 years ago to a PhD thesis that Terry Winograd has written at MIT. It's called Shrewd Law. And this was a communication that his model had with humans about the real world, Block's world. And this was very, very impressive. You can look at this correspondence, and a lot of people said, oh, wow, we solved it. We have a computer program that can maintain a conversation with users about blocks. And it could reason about, can I put this on top of that? Can I move this from here to there? And so on. Of course, Terry knew that this isn't solving the problem because, you know, the world was very small. It was 50 objects or so, very little ambiguities, almost single option for every decision. Now, today, our models can make much better conversations. And I'm showing here the example that I'm sure all of you have seen of Kevin Roose, the tech journalist of New York Times, talking to ChatGPT via Bing. And I'm zooming in so you'll see how good and how fluent the text is and how knowledgeable the model is about various things. So clearly, very, very fluent, smart. I don't know. I mean, at the end of this conversation, the model asked Kevin if he wants to leave his wife and move in with the model. So this is one thing that we have learned. We have learned that being linguistically coherent is much easier than we thought. You take a very, very deep model, you train it on huge amounts of text, trillions of tokens. What you get at the end is a model that is linguistically coherent. And you know, we were trained all our life to equate being linguistically coherent with being smart. And now we project this to the current conversational models. I don't think this is the case. And if you haven't thought about these details, what is trillion of tokens? I mean, an average book has about 200 pages left. There's about 100K tokens, 100K tokens. Trillion tokens basically means 10 million books. It's a lot of information. All of us together will never touch this amount of information throughout our life. So I think we are underestimating what does it mean to read so much text. We as human beings that remember nothing, basically, we are so impressed when models know stuff, but they've seen it. They've seen a lot of it before. And they've seen a lot of stuff that we cannot imagine is even written anywhere. 10 trillion tokens, and all the models are being trained on multiples of trillion tokens. That's a lot of stuff. So we have to think about what are models capable of and what they're actually memorizing, which is actually very good. I mean, it's memorization not in a simple way. It's a very sophisticated memorization that we can access via a very sophisticated and ill-understood similarity function. But this also causes us to kind of misinterpret the model. I'm going to start with one example from a recent work of my students, actually with some people at Microsoft, thinking about hallucination and instruction following. So I'm going to start by something that all of you that work in this area know, that it's very difficult to evaluate models. We don't have the right methodologies today to evaluate generative AI. So one of the goals of this paper was actually to develop some methodologies that will allow us to evaluate better instruction following capabilities and hallucination. And the game we've played here is we start with an example, the one that you see here, you know, when did Athens emerge as an supports the answer to this. And we are perturbing this in two ways. So one way, which you see at the top, I call it answer swapping, is we take only questions that we know the model can answer, open book and closed book. And we change the answer only. We keep the same context, and we just change the answer from, say, the 6th century BCE to the 4th century BCE. So this way, we generated conflict between the parametric knowledge of the model and the context that we are giving it. And we ask the model, use this context to answer the question. That's one setting. The second setting at the bottom, which I call here context enriching, correctly, but cannot answer it closed book. So we know, or we kind of assume, that the model doesn't have this knowledge in its parametric knowledge, or at least cannot access it well. And what we are doing here, we keep the context as is, but we enrich it by adding one paragraph, for example, that is on related topics, but doesn't change the truth value of the answer. It just makes the context a little bit longer and perhaps a little bit more complicated. So what do we see when we do this? So on the left side, you see what happens with answer swapping. On the right side is context switching. context enriching. And what you see, and the gold standard for me here is Amazon Turkers. They are not really gold standard if you worked with this, but still it's sub 10%, and all the models, the good models, are hallucinating here 20 to 30%, depending on the task. So we are not so good at it, despite what we think. What does that mean? Maybe it means that understanding text is much harder than generating text that we have confidence in. Maybe it means that we are too lenient in our evaluation of generation of text, because we look at it, it seems good, we are very impressed, and probably both of these are correct. So with this in mind, let's move on to what I want to focus on most of the talk, which is reasoning. What is reasoning? We don't know anymore. We used to have definitions for what reasoning is maybe 20, 30 years ago in AI. Now we lost this definition, but the way I like to think about it, almost all forms of reasoning boil down to some step of deduction somewhere, and deduction is hard. I'm not going to dive into why and why this is important, but computation, this is a computationally hard task. We can't have very high hopes that everything will be done by these models. But I'm going to give example for multiple types of reasoning to illustrate my point here. And the first example is that of spatial reasoning. I'm going to zoom in so you can see that type of problem. So the cup is on the right of the plate, the spoon is on the left of the plate, the knife is in front of the spoon, and so on. And then I'm choosing two objects, what is the relation between the knife and the saucer. So if I'm going to give you this problem, you will probably read this text, you take a piece of paper, you put the objects on this piece of paper, you look at it and you say, oh, now I know what is the relation between the knife and the saucer. Oh, and amazingly, right. Everyone is very impressed, I'm sure. Why does it get it right? My interpretation here is that it's seen enough things that are similar enough to this. Again, under a very complex definition of similarity. It has seen a lot of things. Well, A is to the left of B, B is to the right of C, C is on top of D. What is the relation between C and D? This is what I call token bias. But we can actually quantify this. We can be impressed with this example, but quantify, and it's very easy to quantify such problems. You can name a few objects, call them A, B, C, D, E, F, G, invent a story, and the story could be something like, and choose random objects and ask what's the relation between them. And when you do quantify this, what you see, for example, for GPT 3.5, between 25 and 45% correct, depending on the difficulty of the problem. So you can be impressed, but nevertheless, it's not good enough. And this has been shown for multiple spatial reasoning tasks for various models, and this is basically what we see here. So let's move to another very important type of reasoning task that we want to be able to do with models, reasoning about sets. I'm going to highlight here one question. Every person in the US is taller than my sister, so I wonder if every person in Alabama is taller than my sister. Now, you can read the answer of the model here. This is kind of nonsense, and to me, that indicates that the model doesn't really understand that what I want here. The answer is simply yes, that's what we need. The rest basically indicates that the model doesn't understand that this is a very simple logical question with a yes/no answer, and that's it. Now we can move to other kind of reasoning about set. This is a quantitative reasoning task where I start by asking for a list of all presidents since 45 and the number of kids they have. There's a mistake for Biden, he has more than one child, but it's correct for Clinton, for example, one child. But then I'm asking a reasoning question with respect to this list, and I'm asking, give me the list of presidents that have at least 2 children. And Clinton is here too. So it clearly contradicts what we've seen in the previous slide. Could be funny, but really reflects a problem with respect to reasoning capabilities. And we can go on and on. I mean, people, I'm sure many of you have played with quantitative reasoning. I'm not going to stop on this. I'm going to give you a summary slide on how models today do on arithmetic operations. This is multiple models, multiple operations, the range of 10 to the minus 5 to 10 to the 5. Models are not doing well. Now, of course, it's not surprising. I don't think we should ask models to do arithmetic operations. And it's a waste of time to try to train them unless you want to learn something about models. But it does give us some information about what is the state of these models with respect to such things. It's perhaps more interesting to talk about scheduling problems. I'm not going to give details here too. Models are not good at these scheduling problems. If you look at it for 20 seconds, you will figure out what is the answer. And even more worrisome is the fact that if you take models and you kind of converse about this, you can get the model to answer any way you want. And it's not surprising, because if we really think about how we train these models, we train the model really very simple, with simple objective, really supervised learning, supervised classification task to predict the next token. And, you know, sometimes we predict the next token with left only context, but, you know, some models are other decoder models, and they look at two-sided context. And to me, this is kind of the key reason we were excited as a community, because we said, oh, old machine learning is gone. We don't need to work so hard on getting data, supervising, and so on. Self-supervision is going to solve all our problems. And self-supervision is really impressive. It does give us a lot of progress here, but we have to realize that that's not what's happening today. I mean, most of the effort today is actually being spent on the supervised fine-tuning of models and alignment of model via RLHF or other things. Actually a lot more expensive than old machine learning supervision, because it's a lot more data, and some of the steps go through the model. The model is in the loop, right? So you run something through the model, you get feedback from the model, you do something with it, you know, you rank it, or you one way or another, and then you give the feedback to the model. But at the end, what we have is a feed-forward model, an autoregressive model that, you know, gets input, feed forwards the model, a token drops back, and these models are kind of limited. So the example that I've given before is not a random collection. There are some tasks that fundamentally we cannot get consistent and reliable answers from these kind of models. You know, this has to do with quantitative reasoning with respect to some special data type like spatial or temporal. A lot of problems that require us to maintain an intermediate representation and reason about it, perhaps with backtracking. And, you know, there is a beginning of some theoretical understanding of where we are with respect to this model. And I'm not going to talk a lot about it. I'm very interested in these things, but, you know, these are really separate talks. So I'm not saying that we cannot solve these problems. What I'm saying is that LLM alone are not going to solve this problem. So we have to figure out how to close this gap between what LLMs can do and where the solutions are. And eventually we're going to develop systems that have LLMs in them. And this is really what I want to talk about. But before that, I want to mention the truth, because this is really important. You know, models, the way we train them today, cannot tell the difference between truth and things that seem true. And really, this is part of the way we train the models, right? So the training process inherently encourages model to hallucinate. I mean, there are many ways to think about it. Perhaps the simplest way to think about it is that when I train model on supervised data and I ask the model who is the first US president, I don't know if the model knows the answer or doesn't, and I'm going to give it an answer. So I'm basically training the model to give me a name of a person given a question, even though it doesn't know whether this is the right name of a person or not. When you do these kind of things at very large scale, what you get is models that basically hallucinate quite often. And I have several examples here. I'm sure many of you have played with such examples of, you know, URLs that do not exist or various other things. There's a few other examples that you can find in one of our recent papers that tries to understand whether models can help us to in the context of kind of various scientific questions where experts are needed. Okay, so I'm going to give one final example in this part where, again, I'm hoping many of you have seen this kind of example. This is called the Wason selection task. Was popularized by Johnson Laird maybe 30 years ago or so in his work on model-based reasoning. What you have here is 4 cards. Each one has a number on one face and a color on the other. You're asked to determine the truth value of the following statement. Now you listen. If a card shows an even number on one face, then its opposite face is blue. And the task is to turn over the minimal number of cards that allow you to determine if the statement is true. I'm not going to stop here and ask you what the answer is. I'm doing this in some of my classes, and I can tell you that computer science are pretty good at it because, you know, we are being trained to do these kind of things. Many people are not good at it. Most people are actually not good at this. But the interesting thing is that if I'm going to give you an equivalent task that is grounded in some familiar situation, people are much better. So for example, if I take PhD students and I'm saying, if a student scores less than 650 in quantitative GRE, then they cannot get into a top CS program. And then I'm going to give you cards that on one side you'll get the GRE scores, on the other side you'll get the program the student is enrolled in. People are much better. If I give people from the street the task of, if a student is younger than 21, they cannot drink beer in the US. And then the cards will have age on one side and buy, cannot buy on the other side. People are much better than it. So what do we learn from this? This is about people. Our model is doing similar things. So I'm going to run through another example that I see that I don't have time to give details on. Football assistant example, but I'm going to get to the bottom line because I'm sure you all understand football well enough, so we don't need these details. But the bottom line that you can take from the Wason selection card and from also the example of the football that makes these things a little bit more concrete, I don't want to get into it now, is that really the world has a symbolic structure. People often, not always, find the symbolic structure and use it to reason consistently. LLMs cannot find the symbolic structure. Sometimes the token bias produces the same response as if they found it. And the second lesson that I want to highlight is that what we've learned over the last couple of years, that often, more often than we thought, token bias is consistent with reasoned conclusions. It's good enough. Now, this is what Daniel Kahneman called, you know, think fast, think slow, system 1, system 2, choose your favorite terminology here. But I think this is not enough. If we want models that support decision-making consistently and reliably, we need them to find the structure and be consistent. I mean, what would you do if your calculator would give you the right answer 70% of the time? So I think our requirements for the model should be different than, wow, look, this is cool. Half of the time it does it. And what are we doing here really? We're doing inductive learning. Inductive learning has some probabilistic guarantees as a function of examples we've seen in the past. And that's good and cool and gives us a lot of sort of advantages sometimes, but sometimes we actually need exact learning of theories. Maybe not for text generation. Maybe text generation is loose enough and we can be happy with what we get if we're carefully reading it, but to support some decisions, we need more than that. So again, I'm bringing back this Wason task. Think fast is basically just predict. Take the input, predict. Think slow means identifying the structure, the constraints, and then reason consistently. This must be 100% correct. And LLMs are doing memorization. Basically, they think fast, and they don't do the reasoning or my definition of reasoning, at least. So I want to give one more example kind of to highlight the difference between reasoning and memorization. And this is in the context of recent work that my students have done. And again, I'm not going to give all the details of this. I just want to highlight one point. So this was done in the context of developing a new data set for question answering about entities. So you start with an entity like Leonardo DiCaprio, and you identify two relations that he participates in from Wikipedia. He produced Gardener of Eden, he starred in J. Edgar. This gives us a question. Which producer of Gardener of Eden also stars in J. Edgar? We can present this to a model. Now we can also focus on one of these entities and keep on going. So I'm taking J. Edgar and I'm looking at relations J. Edgar participates in. It was written by Dustin Black. It was produced by Malpaso Productions. And I can generate a question, which producer of Gardener of Eden also stars in a film that was written by Dustin Black and produced by Malpaso Productions. And you understand the idea here. I can keep on going. I can generate, a chain of more and more complex questions. We generate a data set. Everything is based on DBpedia. We know that the model knows everything. We can even verify that the model knows all the facts. Let's look at the results. So there are two observations. The least interesting to me is the fact that the models are not so good. I mean, there's a big gap between GPT-4, for example, and human performance. The more interesting observation is that, okay, so for one step, the models are better than longer chains, but the results do not degrade with the length of the chain. And this is surprising because you would expect that the longer the chain is, the results are going to be worse. And if you look at it more carefully, we see that actually the accuracy correlates very well with entity similarity. So the way we measure it is we look at the entity in the answer and we measure similarity to entities in the question. And what we see, we should see actually a flat line following, if the models actually are following the reasoning chain, because the similarity of entities makes no difference, right? The model knows all the facts. But what we do see is that entity similarity actually strongly correlates with performance. And that to me indicates that what's important here is not the length of the chains, but rather the similarity of the input to the answer. I'm going to give one example to bring this home. From the same data set, I can ask which producer of Gardener of Eden also stars in film A. Film A is written by, and so on. And at the end of this, and produce Thunderbolt and Lightfoot in 1974. And the answer to this, the model answers correctly, is Leonardo DiCaprio. Now I'm going to ask exactly the same question. The only difference is that instead of the Lightfoot in 1960, same question. All the facts are given. So a model that answers the top one should answer the bottom one. It doesn't. Any idea why? No fans of Leonardo DiCaprio here. So the reason is, I think, he was born in 1974. And this by itself, I think, triggers the model. There's enough similarity of entities to give this answer. And this happens a lot. So what should we do? So my argument is that models on their own are not powerful enough, or not powerful as we think or thought they are. We need to augment models' capabilities, and there are multiple ways of doing it, and I'm listing here a few such ways. So prompts is a very popular way of doing this, chain of thoughts, or just kind of playing with prompts. To me, not an interesting way of doing it. This is basically exploiting the fact that models memorize, which is okay. You can get a few more points, so we can do it. But really, if a model doesn't understand what you want one way, and then you change it a little bit, and now it understands what you want, it basically means that the model doesn't understand well. But still, as I said, if it gives us a few points, let's do it. Post-model reasoning is another way, and I'm including here consistency, verification, and various ideas of how to query models for intermediate results and then do some real reasoning on top of it. I think this is an important direction. I'm going to focus a little bit more in the 5 minutes that I have or something like this on other ways, which is augmenting models via agents, for example, which I think is really a fundamental issue that we have to study more and do more work on. And the way to do this, I think, is to better supervise models so that we can teach them things that otherwise, from the natural input, they will not learn. So here is one example. In Yokneam, in what month of the year is the long? Most of you don't know the answer to this question. I know that some of you do, but all of you have a plan for how to come up with the answer. And the plan in this case is very simple. All you need to know is where Yokneam is. And in fact, you don't need to know exactly where it is. You just need to know which hemisphere it is. And once you know this, you know the answer to this question. Now, of course, if I would ask in New York State, you don't need a plan because this is written many, many times. By the way, the answer for Yokneam is now also written many, many times because I've given this enough times. But the bottom line is that in many, many questions, we need a plan. I mean, so if I show you this image and I'm asking you approximately when and where this was taken, most of you will not know. But all of you will be able to look at the image more carefully, read the signs, and go out of the model and ask some questions, do some search, and you'll figure out what the answer is. If I'm a shopping assistant and I need to serve someone that wants a charger for their phone, again, I need to come up with a plan that figures out, you know, what do I know about this person, about their phone? Do I know something about their phone? How do I build a conversation with them? That's a plan. And, you know, there are many, many other cases where we need, in order to, you know, behave well in the world, I need my model to plan. If I'll ask it, will we make it to the movie? That's a Google Maps question, very easy. I can make it a little bit more interesting. Will we make it to dinner before the movie? And now it's really important, you know, beyond the temporal reasoning that is rather simple, you know, time now, start of the movie. I need to think about the duration of dinner. I need to think about time to get to dinner. I need to think about whether I can afford going to a fancy Japanese restaurant or just Chipotle. I need to think about parking. It's not mentioned here. So there's a lot of stuff I need to think about, and sometimes I'll need to backtrack given answers that I get. And I can make this scenario as complex as I want. The bottom line is that the temporal reasoning itself isn't the issue. I need to be able to decompose the problem. I need to do some planning. I need to do some calling to external models, and that's a plan by itself. And that's challenging. LLMs cannot do it alone. They cannot plan today, and we need to augment them with the ability to plan, to interact, and ground themselves, and so on. What I'm showing here, and you won't see the details, is my attempt to try to use one of the models. In this case, it's a Google model to answer these questions. It fails miserably because it doesn't know now how to ask questions. What questions should it ask in order to make progress on this task? So this is the only AWS slide that I have here. So this is something that we've actually recognized a couple of years ago. We started a framework that we called Dialogue to APIs. Basically, under the assumption or the belief that the key disruption of these LLMs is going to be that they are going to be the new UX. They are going to be able to facilitate interaction with all software systems, hence Dialogues to APIs title. And you know, this effort started long before ChatGPT was out and popularized everything. It helped us push this internally, of course, but basically, I still think that this is where the disruption is going to come. If we are able to talk to all software systems, this will allow us to do quantitative, temporal, spatial reasoning that models themselves cannot do. Of course, in order to do this, we need some rudimentary or more reasoning, the composition, planning capabilities of models. Otherwise, we cannot go out correctly to these APIs, tools, plugins, whatever you want to call them. So now you can tell me, you know what, your thinking is cyclic here. And it is cyclic, right? Because in order to orchestrate, you need some reasoning capabilities, and you just told us that you don't have reasoning capabilities. And you would be right, it is cyclic. But the solution to this puzzle relies on the fact that some learning problems are easier than others. And these easier problems, if we curate data appropriately, we should be able to provide good supervision for them. And I'm going to give just one extreme example to drive this home. So a model that correctly performs a log multiplication is very difficult to train, and definitely to train in such a way that it can generalize across the length of the input. We just don't know how to do it. But a model that generates a small piece of code that calls a calculator on this operation is very easy to do today. And even though this is an extreme example, this is the direction we should go and take. So how do we do it? So I call this effort learning to reason. Really, we have to think about how to identify the structure of the problems and equip models with this. We need to think what are the variables that we have to think about in this problem. Yeah, okay, given the time, let me just skip this and give a quick summary of this example. So basically the idea here is that we should be able to curate data in a better way. And I think what Sebastian has done in some sense relates to this goal, only that we've done several efforts of various types of ways to supervise models with enriched data. The example that I like the most to give in this context is this one on the left. This is Aristotle. Many of you have seen this question already. Did Aristotle have a laptop? If you haven't seen, you already know the answer and you may smile. But the reason I think this is an interesting question, and now a lot of models can do it well because, there's a data set that we put together that is called strategy QA. Models can do, 70–80% on this data set. But really, in order to answer this question, you should be able to decompose it correctly. And all of us will decompose it in about the same time. All of us will think of about when did Aristotle die, about when were laptops invented, which event happened first. How do I teach model to do this? So one of the sort of direction we've taken, develop data sets that are based on comparable text. And basically, we give information to models that doesn't appear in natural text. Example would be in this, the one that, the entry that I have an arrow to. This is a statement about gophers. I don't know if you can read it. On the green side, it says gophers hide in holes and tunnels. On the yellow side, it says gophers are capable of digging holes much larger than themselves. So if I train a model with input, the green input, to predict the yellow output, then what I've taught the model this way is that if you see a statement, or in order to be able to hide in a hole, the hole must be larger than your body. Now, this is not written in natural text because we all know this. And there are many, many dimensions of such things that are not written in text because we all know it, but we can enrich the text various ways and then train models on this, and we get better results. And again, you can look at the papers. And we can do this also in the context of common sense. I'm showing here a cool example, I think, of common sense reasoning that models are not capable of. The picture on the left, the request was a bear eating salmon, and the right is a person eating salmon. And you can see that the bear that is eating salmon doesn't really eating the right salmon that bears eat. That requires some common sense. And we've done such work with data enrichment also in the context of temporal common sense. I'm not going to give the details. But the basic idea is that supervising models with enriched data can be used to force models to attend to signals that otherwise they will not see. Okay, this is my last example. And I'm going to basically talk about recent work on how to help models to reason. Again, I'm going to start with these examples, and you can look at these two examples. One of them is, was Gandhi absent from the 1947 Indian Independence Day celebration? The answer is yes. Was Marie Curie absent from the 1903 Nobel Prize ceremony? The answer is yes again. The model knows all the facts. The model answered correctly in both of them, even though these are two different aspects. The first one, he was just in a different place at that time, couldn't attend. The second one, she couldn't attend because female scientists were not allowed to participate in Nobel award ceremony at that time. And the model knows this. Now, I'm going to present exactly the same question to a model. Was Bruce Lee absent from the 1964 University of Washington graduation ceremony? Again, the model knows all the facts, and we can check and verify that. And it's the same reasoning problem as before, but the model doesn't answer correctly. So it doesn't really perform coherent reasoning the way we want. It basically knows, well, Marie Curie Nobel Award appears a lot of times. And Gandhi and independence appears a lot of time, it gets it. It doesn't get things that have kind of weird or rare combinations of entities. So how do we deal with it? How do we transfer what LLMs do well to a symbolic process that we can then use to solve problems that LLMs do not solve well? So the methodology that we develop, and I want to focus that it's a symbolic process, because otherwise there's no way for us to guarantee consistent reasoning. So how do we move to this? So the methodology is again something that I call incidental supervision. We basically generate simple examples based on the problems that the LLMs can do well. We abstract these problems, we do some divide and conquer, I'm not going to give all the details, and then we use a separate model to learn Python code that solves these problems. And this is easy enough. Most of these are very short pieces of code. And then we can train the base LLM on these pairs that we got, simple problems, Python code, to do better. So as an example, we can start with this Bruce Lee example. We can abstract it. Was a person A absent from event B? And then I can find multiple examples that have this, that are instances of this template. In this case, these are again two different solutions. In the first case, it's temporal. He was in a different place, spatial, I should have said. In the Barack Obama case, he was just born that year. He wasn't there. But then I can generate code. And it's two separate pieces of code that address these problems. And now I can use this. And we generated, a large data set, not large enough perhaps. Everything is automatic. We can generate more pairs, questions, and programs. And now we can use this as a way to solve reasoning problems like that consistently and reliably. So what's the right way to think about this? I'm actually not sure yet what is the right way to think about it. One option is to think about it as teaching the model to solve easy problems the right way. And once they solve the easy problem the right way, as opposed to how they did it earlier, they will solve also harder instances the right way. Or we can think about it as really a way to exploit the fact that models are very, very good in memorization. And we exploit this. Instead of memorizing the tokens, we force them to memorize the reasoning path. And now that they memorize this, they will be able to solve harder problems. I don't know yet how to think about it, but this allows us to kind of support model reasoning beyond LLM capabilities, which I think is where we should be. We're not going to stop there. There's other ways to extend the model capabilities that we have to think about. But I will conclude here. Basically, we all agree that LLMs are making big waves for the right reasons. At the same time, we need to understand the limitations and the advantages that they have. And I try to focus on kind of two lessons that are highlighted, lesson 1 and lesson 2 that you can read here, and looked at it from the perspective of reasoning, orchestration, didn't get so much to talk about retrieval, which is another important use case that we need to learn how to do better. And thank you.
Thank you, Dan. Let's take one question, and then I'm sure Dan will be able to field all of your questions during our lunch, which is right over there. Peter Stone.
Thanks for the talk, Dan. So it sounds like you're advocating basically get more data and from a planner or whatever, and then train the model to do that. But we've known, as you know, well, that there's other AI methods beyond the neural models that have been able to do this for a long time. So why not convert to PDDL and then you call a planner, or why not do sequential decision making with reinforcement learning and have these as
that's exactly what I'm advocating. Go out of the model to agents that will do the calculation for you, the planning for you, everything for you. All I'm saying is that even to reliably go to this PDDL or calculator or spatial reasoner or physical simulators, I need to equip the model with abilities to do it. Today, models are not able to even go out reliably. So there are two steps. First, you're right. Instead of LLMs, we're going to talk about systems of models. They will have planners. They will have many other things. But even the models themselves are not capable today to go to these agents reliably, and we need to do more in order to do this.
So then does the process then continue beyond that to like, once you've done that? So like, I mean, you could do that permanently, always call to the external, or you could turn that sort of system 2 reasoning into chunks that then get re-embedded as system 1. It sounded like you were going into that, going that second step as well. What's the, like,
It will have
where
to be.
should we land?
First of all, I don't have all the solutions. I mean, we are at the beginning stages, but I think eventually there has to be a conversation between base models and other small models that have enhanced capabilities and agents like planners, because it's not just kind of go to another agent and forget about it. Other agents are going to come back with responses. Other agents would like to go to additional agents and talk to them. So it's going to be a system of models, and we should be able to figure out how to deal with it. That's why I talked for a second about multi-agents. That is also something that we'll have to be able to deal with it. Many applications, single agents are not going to do it.
Let's continue this over lunch, and we'll meet back at 1:30. Thanks again, Dan.